going to record the session. We'll post this on the A+ College Ready YouTube channel once we get finished today. If you haven't already muted your microphone and turned off your camera, please go ahead and do that. That makes the system run a little bit more seamlessly. The PowerPoint that I'm using, I'll send that out to teachers here at the end of the day today. And our next one of these, and there'll only be 2 more before the AP exam. The next one is going to be on simple harmonic motion FRQs, and it's going to be a week from today at 2 o'clock. And you can see the join link down there at the bottom of the screen. I'm going to start today, though, with some information about the exam. Last night, the College Board did a webinar, and they told us a little bit more about how the exam is going to work. So I wanted to share that information with you first, and then we'll get into some actual physics. So first of all, your exam date is Thursday, May the 14th. That's at 3 o'clock Central Time. You'll need to log in 30 minutes before then to the exam interface system. So you'll need to log in at 2:30. We'll talk about how you log in a minute. The College Board just yesterday or so posted a testing demo. You can get to that demo at this URL, cb.org/AP demo. What that demo will let you do, it's not really a practice test. It's a practice of using the interface and making sure the interface will work on your computer or laptop or whatever device you're using. So go to that URL, try it out, make sure you can get in, make sure the interface works with whatever device you plan on using on the day of the test. If it doesn't, first thing you should try to do is just update your browser. So download the newest version of the web browser, update it. I would recommend using Google Chrome. If that doesn't take care of the issue, contact your teachers. I sent them a list of like tech help tips yesterday. So hopefully they'll be able to help you if you run into problems. On May the 4th, the College Board is supposed to be sending you an email. Should come to whatever email address you use in your College Board account. That email is going to have some information about the test, probably a lot of what I'm sharing with you today, but it's also going to have in there your AP ID number. You're going to need that AP ID number to access the test. You're going to need to put that number on the top of each page of your answers. So as soon as you get that AP ID number, write it down, keep up with it, make sure you use the correct number. It's important. If for some reason you don't get the email on May the 4th, you can also get the AP ID number by logging into your College Board account. And you can do that at myap.collegeboard.org. So make sure you have that ID number. The next thing, 2 days before the exam, and this will be for each different exam you're taking, 2 days before each exam, you'll get an e-ticket. It's going to come in an email. You have to have that ticket to access the exam. Again, if it doesn't come in your email like it's supposed to, you can log into myap.collegeboard.org and you can access the e-ticket there. There will be a link in that e-ticket for accessing the exam. That's the only way you can get to the exam. Someone's mic is bleeding over. If you make sure your mic is muted, that'll help. Thanks. So again, the e-ticket will provide a link. You click on that link and it will take you directly to the exam interface. And like I said a second ago, on the day of the exam, you're going to need to go there 30 minutes before the scheduled time. So you're going to need to log in by no later than 2:30 p.m. They're going to ask you some questions to verify your ID and get you logged into the system. So you've got to be in by 2:30 on the day of the test. More than likely in that May the 4th email, they're also going to send you what they're calling the AP exam checklist. I'm going to go ahead and share that with you now. If you just Google AP student exam checklist, you'll be able to find it. But I'm going to pull it up and show you some things on this checklist. So this has some directions for kind of things you need before the exam and all that kind of stuff. Notice you can download a printable version of the checklist from this page. Things that you make sure that these are things to make sure you have before the exam. Your 8-character APID number. We already talked about that. Make sure you know your exam day, start time, all that fun stuff. The check-in time, 30 minutes before the exam. They're just wanting to make sure you're prepared and you know when you're supposed to log in. You scroll on down. Some things to check off to make sure you're ready to take the test. Do you have your e-ticket for that specific exam? And again, they remind you how to find it. Make sure it's the right one. Make sure your device is plugged in. Don't depend on a battery. Make sure it's actually plugged into the wall. Like I said, use Chrome. Make sure you're using an updated version of Chrome if you can. Make sure that you practice the exam demo and you know that your device and your browser work. There's a couple of different ways you can put in your answers on this exam. You can type them in a Word doc, or I would recommend a Word doc, and then paste them into the interface. Or you can type them into a document, save that document, and send in the document as an attachment. Or you can handwrite your answers, take a picture of those, and submit the pictures of your handwritten pages. So there's directions on here for how to do all that. As far as required materials go, I would recommend that you have a printed copy of the AP Physics 1 formula sheet. I've sent that out to your teachers. You can also access it online. I also sent out what I call the AP Physics 1 reference sheets or cheat sheet. It's mostly a flipping physics document that has a lot of tips for each unit, but it's about 7 or 8 pages. If you get to the topic that you don't know much about on the exam, it might be a quick way to find what you need. So I would recommend you have your ticket, your formula sheet, and your reference or cheat sheet all printed out ready for the exam. It's a good idea to look over the security guidelines. It's really important that you don't copy anything directly off the internet. It's also really important during the exam you don't call up a buddy and try to get some answers or talk to someone else in the room. My guess is they're going to be able to pick that up with the mic on your computer. They've got all kinds of security protocols they haven't completely described to us embedded in this. You don't want to get caught cheating on this exam. So make sure you are doing all your work. It is open notes. It's open book. It's even open Google, but it's not open another live person. So don't try to make the call. Don't get on a chat. Don't do any of those things to try to answer the questions. Make sure you find a good, quiet place to test where you won't be interrupted. If anybody does have accommodations, like some people, like if you had ADD or something like that, you might have requested additional time on the exam. If you filled out all that paperwork and you got it approved, that time will automatically be added to the time you have on the exam. You don't need to worry anymore about it. It's taken care of if you filled out all the paperwork. So during the exam, some things to know: don't refresh your browser once the test starts. Don't hit the back arrow. That's going to mess you up. So don't refresh. Don't hit the back arrow. Keep the exam question open on your device. There'll be a timer, and it'll give you a warning when time is almost up. The 5-minute warning means you better go ahead and start uploading your answer. If you don't get your answer uploaded before the time is up, you will get 0 points on this test. So you have to make sure that you hit submit before the time is up. If you do happen to accidentally close your browser or you lose internet for just a second, just log back in with your e-ticket and rejoin right into the exam. You'll lose some time, but hopefully it won't be too much. If for some reason during the exam something crazy happens, you completely lose internet, you completely lose power, you get sick, there is a form, and you can see the link to that form there that you can fill out to be able to take a makeup exam. I wouldn't recommend that unless you have to, but it is an option if something crazy happens. And then after the exam, you can log into my AP. You can indicate the college that you want your score sent to. Make sure you do that, because if you don't do it before then, they're going to charge you later to send your scores. You can actually do that now if you want to. All right, so that's the checklist. That's important for you to look at. Another thing that's caused some confusion for folks, when they originally posted the directions for this new exam, they had a typo on some of their materials. And what they ended up having on the second question, they said there was 20 minutes to answer the question and then 5 minutes to upload the answer. That was a typo. The second question, you'll have 15 minutes to answer the question, 5 minutes to upload. First question, 25 minutes to answer, 5 minutes to upload. Only 2 questions. As I already said a minute ago, make sure that you have a hard copy of the AP Physics 1. Make sure you get the AP Physics 1 formula sheet and the A+ Flipping Physics reference sheets. So a couple more things about your test. Again, log in 30 minutes before test time. Use your e-ticket to do that. You'll have to complete some identity information, and then you'll have to wait for the exam to start. Question 1 will start exactly at 3 o'clock. You'll have 25 minutes to answer that first question. You cannot move on to the next question until that time's up. So 25 minutes, 5 minutes to upload, hit go. When time is up, the screen will automatically go to question 2. You'll have 15 minutes to answer question 2, 5 minutes to upload your answer. So before I move any further, any questions about the exam? Please make sure that you get online and you try that demo just to make sure that your device works. You can access everything. You have no problems uploading documents through that interface. You want to be familiar with the interface before exam day. I would recommend go ahead and doing that today just to make sure it's not an issue. All right, so we're going to work some circular motion problems. And I'm going to skip ahead a bit here. I think I'll start right here. We're going to start with some non-FRQs, and then we'll end with an FRQ. So this one says if the distance between 2 objects is increased by a factor of 8, while the mass of each object is increased by a factor of 4, how is the force of gravity between the 2 objects affected? Give a numerical answer. So what you guys have got to remember is that the force of gravity, the equation for it, Newton's law of universal gravitation, is the universal gravitation constant times the mass of the first object times the mass of the second object over, sometimes this is going to be written as R, sometimes as D squared. That R is the distance between the 2 centers of the objects. So let's say we start with a certain amount of gravity, and now we increase the distance by a factor of 8. So we're going to take this R and we're going to multiply it by 8. Now don't forget, that whole thing is squared. And then we're going to increase the mass of each object by a factor of 4. So M1 is now going to become 4M1, and M2 is going to become 4M2. So now if we simplify this a bit, on top we've got 4 times 4, so we got 16 on top. And on the bottom we've got 8 squared, 64. Well, we can reduce that to 1/4. 16 over 64 is 1/4. What I'm hoping you see this means, don't say that the force of gravity was decreased by 1/4. That's not the answer. The new force of gravity is 1/4 of the original force of gravity. So my answer would be the new force of gravity after the changes is equal to 1/4 of the original force of gravity between the 2 objects. All right, so here's another one. Well, so we've got a satellite orbiting the Earth. We've got the orbital distance between the two. It's the distance between their centers, so that's r. If the satellite must maintain a constant distance from the Earth, what is the satellite's orbital velocity in meters per second? What is its period in seconds? So they love to ask this kind of question. So the way you would do this is you've got to realize that when let's say we have Earth, here's Earth, and then here's a satellite. What keeps that satellite going around the Earth is the force of gravity pulling on that satellite. It's pulling it toward the center of its circular orbit. That force is a centripetal force. And that force is provided by the force of gravity. So the key to working this kind of problem is to set the force of the centripetal force equal to the force of gravity between the two objects. Now, I'm hoping you guys remember that centripetal force is mv squared over r. So this will be the mass of the satellite in this case, v squared over r. And the force of gravity equation, again, is g times the mass of one of the objects, we'll call it mass of the satellite, times the mass of the Earth over r squared. So we're trying to find the velocity. So let's solve this out for v. So first thing I'm going to do is multiply both sides by r. Cancels over here. One of these cancels with one of these. So now that leaves me with ms v squared equals g ms me over r. Only one of those canceled out. So now I can see that I've got mass of satellite on both sides. So those cancel out. And what I end up with is v squared equals g mass of satellite, mass of Earth over r. And then to solve for velocity, I'm just going to take the square root of both sides. So v equals the square root of g. And this, we don't need this. This canceled out. G times the mass of the Earth over r. So that's our equation. We have all the variables we need to plug in. We know the mass of the Earth. We know the orbital distance. And big G is the universal gravitation constant, which you'll find on your formula sheet. Here I have it all worked out. So we end up with a velocity of 8.15 times 10 to the third meters per second. Now this problem also asks us to find the period. Let me make some space here. To find the period equation, you're going to have to do a little bit of substituting. Something that I hope you remember and make sure that you know before the test, we're going to see this on an FRQ a little bit later, is for circular motion, the velocity of something going in a circle can be calculated this way. 2 pi r is essentially the circumference of the circle. So how far is it around the circle? And then the t here is the period. That's the time it takes to make one loop one time around the circle. So what we're going to have to do is we're going to have to take this and we're going to have to substitute it up here for v. That'll allow us to solve for period using that same equation. So let's write out what we've got. So we got 2 pi r over t equals to the square root of g me over r. Now we're trying to solve this for t. So the first thing that I would do is just go ahead to get rid of that radical to make it easier to square. I'm going to square both sides. So when I do that, when I square the left, I end up with 4 pi squared r squared over t squared. And then when I square the right side, I just end up with g me over r. All right, I'm trying to get t by itself, so I need to go ahead and probably multiply both sides by t squared to get that off the bottom. So it's going to cancel over here, give me t squared on this side. Again, I just multiplied both sides by t squared. now I need to get rid of the R's and the G's and the ME's. So let's multiply both sides by R. It'll cancel over here. And when we multiply the left side by R, this R squared is going to become R to the third. Then we need to divide both sides by GME. Cancels over here. So now I take the square root of both sides. Whoops. That's G times ME. And now I have an equation that will let me calculate the period of this satellite, the time it takes for one rotation. Or I really didn't have to do that at all. I could have done what the question says here. Once I already know that velocity, I could have just set it equal to 2 pi r over t and solve for t. Either way will work. What we end up with is 4.62 times 10 to the third seconds. And again, that's the time for the satellite to go one time around the Earth. All right, let's look at this one. So a planet has 3 times the mass of Earth and 5 times Earth's radius. The magnitude of the gravitational field near the planet's surface is. All right, so first of all, you need to think about, well, how do you get the gravitational field of something? And the easiest way to do that is to take the mass of an object, the weight of an object, mg, and set that equal to the gravity equation. Something like so. So this is a mass of an object on the surface of a planet, this m over here on the left. Notice that's on both sides. So that's going to cancel. So we end up with little g equals the universal gravitation constant, big G, times me over r squared. This, a lot of times you think of it as acceleration due to gravity, but this is also called, this is the magnitude of the gravitational field, G. So if a new planet has 3 times the mass of the Earth, so put a 3 here, 3 times me, and 5 times the radius. So let's 5 times the radius. We got to square that. So G is going to be equal to 3 over 25 of the Earth's G. Well, we know G for Earth is 10. So 3/25. 3/25 of 10. And that's going to end up being 6/5 is going to end up being the magnitude. So take 10, regular G, multiply it by 3/25. That would give us 30 over 25, which reduces down to 6 over 5. Gravitational field strength is measured in newtons per kilogram, which is the same as a meter per second square if you reduce everything down. All right, here's another one. So 2 pieces of space junk of equal masses are in circular orbits around the Earth. Object A has a speed of v. The orbital radius of object B is 16 times that of object A. What is the speed of object B? So again, if you don't remember that equation for velocity, you're going to need to derive it again. Remember, to do that, you've got to say, well, the centripetal force keeps the object going around the Earth, and that centripetal force is caused by the gravitational force. Centripetal force is mv squared over r. Gravitational force is g, mass of object, mass of Earth over r squared. Solve that out for velocity. So the masses cancel, the mass of the objects. You're going to need to multiply both sides by r. That's going to cancel out this r right here. So we end up with v squared is equal to g me over r, which means v equals the square root of g me over r. So the original satellite has a velocity of v. The new one is 16 times away, 16 times further. The radius is 16 times as much. So if we put 16 right here, notice we take the square root of that 1 over 16. Well, that's going to give us 1/4. So I'm hoping that you see that the new velocity is 1/4 of the original velocity. So our answer D is the correct answer. Does that make sense to everyone? Any questions on that one?
Where do I find the mv squared over r formula?
Say one more time.
Where do I find the mv squared over r formula?
Okay, so you have a on your. Are you looking at the formula sheet, the Physics 1 formula sheet?
Yeah.
All right, so you have an equation on there, I think, that says AC equals V squared over R. Do you see that one?
AC over.
AC equals V squared over R.
Oh, there it is. Yeah, I see it.
All right, so that's centripetal acceleration. And what you got to think about when something's going in uniform circular motion, the net force that makes it go in that circular path is the centripetal force. So this is an acceleration. So what the way I derived mv squared over r is that this is the equation for the net centripetal force acting on an object. Remember that net force is m times a. So mass times this a. So mv squared over r. Does that make sense?
Yeah.
So it's just the net force acting on an object in uniform circular motion. So take the mass times this acceleration, v squared over r. And that's something that, I mean, you can annotate your formula sheet. I would just go ahead and write it down on your formula sheet that centripetal force equals mv squared over r. That's completely legal on this year's exam. So if I were you guys and I was taking the exam, I would take all kinds of notes on my formula sheet. Anything that will help you out, put it on there. It's completely legal on this year's test. All right, so let's go ahead and look at this problem 6. So a satellite orbits a planet in a circular orbit. The mass of the satellite and the distance between the center of the satellite and the center of the planet are known. What additional information is needed to calculate the speed? So this is another one of those situations where if you don't remember that velocity equation, you'd need to derive it. If I were you, I would go ahead and write the velocity equation on my formula sheet, but we'll derive it one more time. Remember, centripetal force keeps an object going around a planet. That centripetal force is provided by the gravitational force. The centripetal force is the net force acting on the object, mv squared over r. And that's equal to big G times m times the mass of the planet over r squared. Solve this for velocity. The masses cancel on each side. This r is going to cancel out one of those r's. So we end up with v squared equals G times the mass of the planet over r, which means v equals the square root of G, mass of planet over radius. That equation, I would go ahead and write on my formula sheet. And also make sure that you realize that square root goes all the way down. That covers the whole quantity. So if you look at this equation, it says we know the mass of the satellite. We know the distance between the centers of the two objects. So that's this. Big G is the universal gravitation constant. Well, that's on your formula sheet. So you got that. What you don't know that you need to know to calculate the velocity is the mass of the planet that the object is rotating around. So our answer here would be C. So derive the equation, see what you're missing. G, you always know. It doesn't matter where you are in the universe. The universal gravitation constant is the same. R, they gave you in the prompt up here. What you didn't know is the mass of the planet. All right, let's look at this one. So a person who weighs 1,250 newtons on Earth travels to another planet that has 3 times the mass of the Earth and 4 times the radius of the Earth. What is the person's weight on the other planet? All right, so really what you got to think of here is that, well, weight is caused by gravity. And so you just need to take the gravitational equation. Like so. So it says the new planet has 3 times the mass of Earth. So we're going to put a 3 right there in front of mass of the Earth and 4 times the radius. Let's put a 4 right here. Don't forget to square it. So if we simplify that out, we end up with 3/16. What that's telling you is that the gravitational force on this new planet is 3/16 of the original gravitational force. So you need to take 3/16 of the original weight of the person. 3/16 of 1,250, and you end up with 234 newtons. So your answer would be B. What you had to do to work that out is you had to realize that weight is caused by the force of gravity. Plug into the force of gravity equation, get what fraction the new gravity is compared to the original, multiply that by the original weight. All right, now we get into a little bit of uniform circular motion. Let's think about uniform circular motion for a second. So uniform circular motion is when an object is moving at a constant speed in a circle. That's the uniform part. Even though it's moving at a constant speed, it's always accelerating. Because remember, velocity is not just speed. Velocity takes into account speed and direction. Well, if something's going in a circle, it's always changing direction, even if its speed is the same. So what causes it to accelerate? We know that what causes anything to accelerate is a net force. When things are in uniform circular motion, the net force is always the centripetal force. And centripetal, the word centripetal means center seeking. So centripetal forces always act toward the center of the circle. So let's look at this question and see exactly what it's asking us. So we've got a ball, we're whirling it on a string. It's undergoing uniform circular motion. Which of the following best illustrates the direction of the velocity of the ball at point X? So the ball is going to come around the circle like this, and we're wanting to know what's the direction of the velocity at this point, point X. Well, the way you figure that out is you take you go to the center of the circle and draw in a radius to that point. Our ball is rotating counterclockwise. So when it gets to this point, its velocity is always at a 90-degree angle to the radius. So here's a radius, here's a 90-degree angle. So what we're saying is if at this point X, the string broke, the ball would go off in exactly this direction at a 90-degree angle to this radius. So our answer on this one is C. Questions on that one? All right, the next problem looks kind of like the same problem, same situation. This time we want to know which of the following best illustrates the direction of the net force at point X. So again, ball's going counterclockwise. It gets here. Go to the center, draw in a radius straight to that point. Here we're asking about the net force. Remember that net forces, when we're going in uniform circular motion, are always centripetal forces. And that centripetal forces always act straight toward the center. So at point X, the force is going to act directly toward the center of the circle. So we're talking about A being our final answer on that one. And then 10 also looks like the same kind of thing. This time, though, we're asking for what's the acceleration at point X. So again, get to this point, drawing a radius. Even though the speed isn't changing, the direction always is. And centripetal acceleration is always in the same direction as centripetal force, because centripetal forces cause acceleration. The centripetal force is acting toward the center of the circle, which means the centripetal acceleration also has to act toward the center of the circle. So A is what we're looking for there as well. Can I answer questions on any of those for any of you guys? All right, I'm going to work one more problem and then we'll do an FRQ and we'll call it a day. This one can be a bit confusing. So two bags contain an equal number of identical masses. The two bags are separated by a distance r. 1/3 of the masses from one bag are moved to the other bag. If the magnitude of the original gravitational force between the two bags was F, so that's how much force there was before they moved, what's the magnitude of the gravitational force after they were transferred? So before, F would have been big G times first mass times second mass over r squared. That would have been the original force between the two objects. All right, so what we're doing first is we're moving 1/3 of the masses from one bag to the other bag. So if M1 was 1 M1, well, let's say that's the bag we take 1/3 out of. So now instead of M1 being 1 M1, it's going to be 2/3 of M1 because we took a third away. And that extra third got added over here. So M2 started out as 1 M2, but now it's got an extra third. So it was 3/3 or 1. Now it's 4/3 times M2. So now if you simplify a bit, I'm hoping that you see that 2 times 4 is 8, 3 times 3 is 9. So that's hopefully telling you that the new force of gravity between these two objects is 8/9 of the original force of gravity. So we're looking at answer D. So where the mass is at matters. Even though the total mass of the system didn't change, where the mass is at, which object contains the mass, helps to determine the force of gravity between the two objects. All right, so before we go further, I want us to look at this FRQ. Let me blow this up a bit so you can see it. And I'd like for you guys to take just a minute or two and read everything you can see on the screen there. All right, so we've got a spacecraft going in a clockwise orbit around Earth, radius of r. First of all, it wants us to draw and label the forces, not components on the spacecraft. it specifies each force must be represented by a distinct arrow starting on and pointing away from the spacecraft. And notice it says draw and label. So that's important. So let's go here to the spacecraft. Think about the forces acting on it. And really the only force acting on it is the centripetal force, which is the gravitational force, the force of gravity between the planet and the satellite. So I would go here to my satellite and I would draw an arrow pointing right straight toward the planet. And I would label that as F of G, the force of gravity between the two objects. We'll look at the grading rubric in a minute, but I think you got a point for the arrow and a point for F of G. Second part, derive an equation for the orbital period of the spacecraft in terms of M. Let me blow this up a bit so I can see it better. In terms of M, the mass of the Earth, the radius, and physical constants as appropriate. If you need to draw anything other than what you have in part A, use the space below. Don't add anything to the figure. So we derived this equation for period a minute ago. We'll rederive it again. Remember that what causes a planet to stay in orbit, or in this case, the satellite to stay in orbit, is a centripetal force. And that centripetal force is provided by the gravitational force between the two objects. Centripetal force is the net force acting on the object, which is mv squared over r. That's equal to the gravitational force, which is g, mass of the object, mass of the Earth or the planet over r squared. Let's first of all solve this out for velocity. That's the easiest way to go here. So let's multiply both sides by r. Mass of the object, the satellite in this case, cancels because it's on both sides. So we end up with v squared equals g me over r, which means v equals the square root of g me over r. All right, so that's the speed. That's not what it asks us for. It asks us for the orbital period. So what we can do now is remember that v equals 2 pi r over t. We can plug that in. So we can say 2 pi r over t equals the square root of g me over r. And then we can solve this out for t. So square both sides. And you would want to show all this work as you're going. So you would want to show everything that I've shown here. I'm going to multiply both sides by t squared. So it's going to cancel over here on the left. Multiply over here. Okay, now I've got to get rid of the r on the bottom. So I'm going to multiply both sides by r again. This is going to become r cubed. It's going to cancel over here. And then I'm going to divide by GME. And I'm running out of space. But I'm going to end up with 4 pi squared r cubed over GME equals t squared. I need to take the square root of both sides. And what I end up with is this. T equals the square root of 4 pi squared r cubed over GME. So it takes a while to get there, but you would want to make sure you show all that work, derive it down, get your equation. I'm going to have to erase a bit here. So next it says a second spacecraft of mass 2m is placed in a circular orbit with the same radius. Is the orbital period of the second spacecraft greater than, less than, or equal to the orbital period of the first one? So if we look at our orbital period equation, what I hope you see is that the mass of the satellite isn't in that equation. That should tell you that it doesn't matter. It doesn't affect it. The mass of the satellite doesn't affect the period. That tells you that they should be equal. And the way that I would briefly explain my reasoning is I would say that according to the equation, write this equation down. The mass of the satellite does not affect the orbital period of the satellite. That would be all you would need to do to briefly explain your reasoning. Now let's go ahead to the next slide. Here's the last part of this equation, or this question rather. Let's blow this up. Oops. All right, so this said the first spacecraft is moved into a circular orbit that has a radius greater than r. So we move it away from the planet, essentially. Is the speed of the spacecraft in the new orbit greater than, less than, or equal to the original speed? So just a second ago, let's backtrack. We derived this equation for speed. Let's take that and put it on the next slide. That's the speed of a satellite in essentially in uniform circular motion. So we want to know if we increase the radius, what happens to the speed? Well, notice where radius is in our equation. So if this gets bigger, since it's on the bottom of the fraction, the velocity is going to get smaller. So is the speed of the spacecraft in the new orbit greater than, less than, or equal to the original speed? Well, it's going to be less than. And I would say in the equation for velocity, and I would write down that equation, since radius is on the bottom of the fraction, if the radius increases, the velocity decreases. So you could answer the whole question in 1, 2 good sentences at the most. Let's look at the grading rubric real quick, the scoring guidelines, just so you see what they were looking for. Notice on the first part, we were supposed to draw the force and label it. So 1 point for an arrow toward the center of the Earth, and then 1 point for a label showing that it's the gravitational force. So 2 points for that. Easy 2 points. Next part of the question. So deriving that equation. 1 point for coming up with a whole mv squared over r and setting that equal to, and the type here is messed up, but essentially that's saying that you're realizing that there's a net force. That net force is mv squared over r, and it is caused by the gravitational force, g m me over r squared. Got a point for that. You got another point for deriving the equation for velocity, or simply writing down v equals 2 pi r over t. And you got a third point for filling that into the velocity equation and solving out for the period. 4 pi squared r cubed over g me. So there were a couple different ways to get those points, but 3 total points on part B. And then finally on part C, this is the one where you move the spacecraft out. You first of all had to say, I'm sorry, this is the part about the period. So the period you had to say is the same because the period is not affected by the mass of the satellite. So you didn't get any points for saying equal. You got a point for saying they're equal because the equation for period does not include the mass of the satellite. All right, and then the final part, this one. So the first spacecraft is moved into a circular orbit that has a radius greater than r, as shown in the figure below. Is the spacecraft in the new orbit, is the speed of the spacecraft greater than, less than, or equal to? So here you had to say less than. There was only 1 point available here, so you had to say less than because The radius is on the bottom of our equation for velocity, g(m)e over r. And when the radius increases, that causes a decrease in speed. All right, that's it for today. Can I answer questions for anybody? Make sure that in the next day or two, you go to cb.org/apdemo, and you make sure that the demo interface works with your device you're going to use on the test. Also, make sure you go and look at the checklist and you're familiar with everything that you need for the exam. Go ahead and print out your formula sheet, print out your reference or cheat sheet, making sure you have that on hand. Also, I'd go ahead and find my AP ID and make sure that I know what that is and that I have it so I can easily access it. Just to be on the safe side, I would also log into myap.collegeboard.org just to make sure you could get in. That's just in case you don't get the email with the e-ticket. You can go here and you can access your e-ticket. All right, that's it for today. Thank you guys for being here, and I'll